Okay, so we are going to continue with refraction of light. Refraction of light. All right. So previously we already got discussed a bit about refraction of light. It is exactly same or almost the same lah, like all the other wave. All the wave can undergo refraction. So refraction of light. What is refraction of light? Refraction of light is change in direction of light due to change in velocity of light when traveling through medium of different optical density. So same with other wave. Other wave will also change. The velocity of the wave will also change when something happen to the medium. Okay, when something happens to the medium, for example, water wave will become slower when the depth of water changes. Okay, when the depth of water become deeper, the water wave will be able to propagate faster, and when the water become more shallow, then the water wave will propagate slower. And sound wave also same thing. Sound wave become faster when the temperature of the medium increase, when the density of the medium increase. So for example, the density of gas, density of liquid, density of the solid is higher, then the sound wave will be able to propagate faster. Okay, and the other way around. Okay. Okay, so what happens when the speed of the wave or the velocity of the wave changes? What changes is the direction. Okay, direction will change. So this phenomena where the direction of the wave change is what we call refraction of wave. So here we are talking exclusively about light. So it is refraction of light. Okay. So one more time, okay, refraction of light, change in direction of light due to change in velocity of light when traveling through medium of different optical density. So what is optical density? Okay, previously in lower form science, when we learn about refraction, we only say that when the medium travel between different density, okay, different density, that refraction of light will occur. Okay, we don't talk about optical density. So here we want to be more specific that it is actually different optical density that make the speed of light changes. And when speed of light change, direction of the light can change, and this is what we call refraction of light. Okay, so what is optical density? So optical density is not the same as density, which is defined as mass per unit volume. Okay, so this is density here. Okay, mass per unit volume. So, for example, density of oil is lower than water, but optical density is higher than water. So this can show us that optical density and the density is different. Okay, they are not the same thing. Okay, so example here we have glass block. Okay, we have a piece of glass block. So incident ray is the light ray that going towards the different medium. Okay, propagating in one medium and going into a different medium. Okay, we call it incident ray. Okay, the light ray. Okay, since this point where the light ray go into a different medium, okay, this is what we call a point of incident. Okay, and the light ray that inside the medium, inside another medium, that is being refracted, we call it the refracted ray. And then the light ray will come out from that medium, and we call it the emergent ray. Okay, so because air, okay, here we have air and glass block. So air have lower optical density compared to glass block. Okay, glass block have higher optical density. So what happens is the speed of light will decrease. When the light slow down, the light will undergo refraction and it will refract towards the normal. And then when the light come out from the glass block into air, that means it go from high optical density to low optical density. So the speed of light will go back to the original. Okay, that means as long as it's inside air, then the speed of light will be the same. Okay, that means it can return back to its original speed of light. And when the light go from air back to vacuum, let's say if the light continue to go and then go back to vacuum, then the speed of light will go back to the original speed of light, which is 3 times 10 power by 8 meter per second. Okay, so that is the maximum speed for light lah. Okay, so this symbol I is the symbol for incident angle, and R is the symbol for refracted angle. So when the light go from low optical density to high optical density, then the refracted ray, the refracted angle will be smaller than the incident angle. Okay, and if the light go from high optical density to low optical density, then the incident angle will be smaller than the refracted angle. Okay, incident angle will be smaller than refracted angle. Okay, so we go through this. Okay, light ray travel over here. Okay, light ray travel from medium or low optical density to medium or high optical density. So speed of light decrease. Light ray bend towards normal. Angle of refraction are smaller than angle of incidence. And then here, what happened over here? Light ray travel from medium of high optical density to medium or low optical density. Speed of light increase. We say increase, but it go back to the same speed as this one here lah. Okay, this one is inside air, this one also inside air. Speed of light increase, so that means from here to here it become faster lah. Okay, speed of light increase. Light ray bend away from normal. Angle of refraction larger than angle of incidence. Okay, so we know that different medium have different optical density. So how is it that we can compare the different optical density? Which one have higher optical density? Which one have lower optical density? We know that if the optical density of the medium is higher, then the light that go into that medium, the speed will decrease even more. Okay, that means high optical density, lower speed of light. Low optical density, then the speed of light will be higher. Okay, so how do we compare all these medium of different optical density? We use a value that we call the refractive index. Okay, the symbol of the refractive index is a small n. Okay, refractive index of a medium is a ratio of speed of light in vacuum to speed of light in the medium. Okay, so this is n is a refractive index equals to speed of light in vacuum over speed of light in medium. So basically, this is the number that compare the changes in the speed of light when go into the medium from vacuum. Okay, we want to compare the changes in the speed between vacuum and medium. So speed of light in vacuum is the fastest. Okay, nothing can go faster than speed of light in vacuum. And that means speed of light in medium will definitely be lower than speed of light in vacuum. So the refractive index of any medium will definitely be a number that is larger than 1. Okay, so like what is written here. Okay, since speed of light is highest in vacuum and lower in any medium, refractive index of any medium is always greater than 1. Okay, always greater than 1. So this can act like a way for you to to know whether your calculation is correct or not lah. For example, if you want to calculate refractive index and then you find that your answer is less than 1, then you automatically know that something is wrong with your calculation. Okay? Because refractive index for any medium cannot be lower than 1. Okay? Cannot be lower than 1. It can be the same. It can be same as 1. So what is it? What medium have the refractive index of 1? It's vacuum lah. Okay? Vacuum is the medium of light that have the lowest refractive index, which is 1. Why? How is it that we can get 1? So if the light is propagating in vacuum, so that means to calculate the refractive index of vacuum, you take speed of light in vacuum, divide by speed of light in the medium, and the medium is the vacuum. So speed of light in vacuum over speed of light in vacuum. So you get 1. Okay? Get the idea. So 1 is the lowest refractive index. There's no refractive index that's lower than 1. And number 1 is refractive index 1 is vacuum. Okay? Anything other than that will definitely be greater than 1. Okay? So this is speed of light, 3 times 10 power by 10 meter per second, which is extremely fast. Alright. So refractive index of a medium is greater when medium has greater optical density. So if the medium have larger optical density, so of course the refractive index will be larger. Wavelength of light is lower. That means if the light is blue color, that means shorter wavelength. Then that means the light, when go into a medium, it will become slower. And red color light have long wavelength. So when you go in the medium, it will be faster. Okay? So long wavelength can go faster in the medium compared to short wavelength of light. Okay? You get the idea. That means like this. Okay, that means for example, okay, so we have a block of glass. Okay, so we have okay, that means like this. Okay, let's say that this is a block of glass. Okay, so if we have red light, okay, if we have red light, okay, if we have red light go inside, okay, go inside the glass, the speed of light will decrease and it will refract towards normal. Okay, the light will refract towards normal. Okay, refract towards normal like this, for example. Okay, and let's say that we have blue light. So this blue light go in at the same angle as the red light, and it will also refract, but it will refract more. The angle of refraction will be smaller. Okay, it refract more, so that means the refracted angle is smaller. Okay, let's say that okay, this is the normal. Okay, let's say this is normal. Normal, usually we use dotted line. Okay, dotted line. Okay, normal is 90 degree, okay, with the border. Alright, so you can see that this angle of incident and this angle of refraction, compare with this angle of incident and this angle of refraction. So let's say this angle is the same lah. Okay, these two angle is the same. Okay, but this one, the angle of refraction for blue light will be smaller because the blue light refract more. Okay, so it's like this: blue light have shorter wavelength. Okay, this is something that we learned in previous topic lah, where we learned that light of different color have different wavelength. Okay, light of different color have different wavelength. The red color light is longer wavelength, and then go towards the color transition towards blue or violet, then the wavelength will become shorter and shorter. Okay, blue is the longest, and then orange is short a bit, and then yellow, green, light blue, blue, purple. Okay, so purple have the shortest wavelength. Okay, so blue light have shorter wavelength. Shorter wavelength, that means when you go into medium, the speed decrease more. Speed decrease more. That means it becomes slower lah. Okay, slower than red light. So blue slower than red in medium. So in this case is the glass lah. Okay, in this case the glass is the medium. So the blue light will be slower than red in medium. So that means the blue light refract more, or it says, or bend more towards the normal. Okay, blue refract more or bend more towards the normal. So angle of refraction. Okay, angle of refraction of blue light is smaller than red light. Okay, get the idea. So blue light have shorter wavelength, so the speed will decrease more. Okay, so blue will be slower than red in the medium. So blue will refract more or bend more towards the normal. So angle of refraction of blue light is smaller than red light. Okay, you can see the connection. Okay, I hope that you don't memorize blindly lah, but you make the connection yourself. Okay, but you make the connection yourself. Okay, blue short wavelength. So when you go into the medium, it will move more slowly compared to red. So if move more slowly, that means it can refract more. Refract more, that means angle of refraction will be smaller. Okay, so you need to be able to make that connection. Okay, so example, okay, I write in symbol. So okay, so these two angle is the same, but the angle of refraction for blue will be smaller than angle of refraction of red. Like that. Okay. Okay, I get the idea. So the wavelength can affect the refractive index. Okay, understand? That means the glass is the same glass, but the refractive index will be different. Refractive index is smaller. Refractive index in blue, when the light is blue, I repeat one more time, the refractive index for the glass, when you calculate using blue light, the refractive index will be larger than the refractive index of the glass when you calculate with red light. Okay, get the idea? Okay, refractive index of the glass is the same glass, but when you calculate the refractive index using a blue light, then the refractive index will be larger because the speed of light for blue light is lower compared to red, so it will make the refractive index to become lower compared with when you use a red light. Okay, get the idea? Okay, so that means, in conclusion, wavelength of light can affect the refractive index of the glass. Okay, it can affect the refractive index, but there's no change to the glass, no change to the medium itself. Only the number is different because you calculate with different light of different wavelength. Okay, like that. All right. Okay, so okay, wavelength of light is lower. Blue short wavelength, so slower in medium. Red long wavelength, faster in medium. And then the last one is temperature. Okay, if the temperature is lower, then the refractive index will be greater. Okay, refractive index will be greater when temperature is low. So you can help yourself remember all of these factors that can affect the refractive index just by using, okay, you think logically. Okay, you think logically. Okay, so what is it that can, how you calculate refractive index? You calculate by using the speed of light, right or not? Okay, speed of light in vacuum and speed of light in medium. Okay, so you can think like this. If the optical density high, okay, you can think of it logically, to help you remember what are the factors that affect the refractive index. Okay, you can think like this. To calculate the refractive index, you use speed of light in vacuum compare with speed of light in the medium. So that means what? That means if the speed of light in the medium is lower, then you will get a bigger refractive index. And what is it that can make the speed of light become lower? Okay, so you can see when the optical density is higher, then the speed of light in the medium will be lower. Right now, okay? For example, glass have higher optical density compared to air, so the speed of light will be lower in glass compared to inside the air. Okay, so second is wavelength of light. Okay, wavelength of light. So you can think like, okay, if the wavelength of light is short, okay, short, difficult to pass through. Why difficult to pass through? Difficult to propagate through medium. You can think like this. You can think that when we learn about electromagnetic wave, when we learn about wave when we learn about wave, we got learn about diffraction, okay, we got learn about diffraction. Okay, when the wavelength is short, difficult to diffract, okay, don't have the effect of diffraction is lower, okay, and less effect of diffraction. So and we also learned that wave, for example, like sound wave. If you still remember, we discussed about sound of elephant. Why elephant use infrasonic sound? That means sound with very low wavelength. Low frequency, so that the wavelength will be higher. Longer wavelength, it can propagate faster. Propagate not faster propagate further distance. Okay, go further distance. Because of diffraction, it can diffract, pass through obstacle. Okay, it can pass through and pass over the obstacle. Okay, when the wavelength is longer, and when the wavelength is shorter, then it will be easily blocked by obstacle. Okay, wavelength of light, short, it will be easier to be blocked by obstacle. So difficult to propagate through the medium. So it will be slower. Okay, slow. Okay, slower. Wavelength of light, longer, then easier to propagate through medium, then it will be able to propagate faster. Okay, propagate faster inside medium. Okay, you get the idea. So you connect like this. You connect with what is it that you already learned previously. Okay, Okay, and then the last one is temperature. Okay, temperature low. That means what? If temperature low, then the density will become higher right now. Okay, all the particles are all packed together if the temperature is low. Okay, all the atom, molecule all packed together. Okay, all closer to one another. So we can think of it like if the temperature low, the medium contract, all very close together, so the density increase and make the optical density, make the optical density become higher. So when optical density become higher, so the speed of light will become lower. Okay, so you can see here that you have to think of what is it that can affect the speed of light. So this one, speed of light lower, so that means the refractive index will be higher. Okay, when speed of light lower, then refractive index will be higher. So that means temperature low, speed of light in the medium low, so refractive index of the medium will be higher. And then if you use the wavelength of light that is shorter, then the light will be slower, then the refractive index will be higher. Okay, and this one, optical density higher, speed of light lower, so refractive index higher. So you see or not? Okay, you have to connect like this lah. Okay, speed of light in the medium low, refractive index high. Speed of light in medium low, then the refractive index will be high. Like that. So what is it? So you have to think of what is it that can affect the speed of light in the medium. So whatever is it that can change the speed of light in the medium, then that means it will also be able to change the refractive index. Okay, get the idea. Okay, so refractive index of medium is greater when medium has greater optical density, wavelength of light is lower, temperature lower. Okay. Okay, so we look at example here. We have different medium, vacuum and air, olive oil, and so on, and their respective refractive index. Okay, so vacuum and air is the lowest refractive index. Air, because air have very low refractive index, almost the same as vacuum. So we take it as 1. Okay, we take it as 1. If I'm not mistaken, it's like 1.002, the refractive index of air. Okay, the refractive index of air, if I'm not mistaken, is 1.002. So that means if you round off, then it becomes 1.00 lah. Okay, so we take that the refractive index of air is the same as vacuum. Olive oil 1.46 perspex. Perspex is a type of hard plastic. Okay, it's a type of plastic. Okay, perspex is a type of plastic. Okay, 1.5 glass, crown glass 1.52, flint glass 1.66. Okay, they are both glass, but they are different type of glass. Okay, they are different type of glass. Diamond 2.42. Actually, diamond is the diamond have the highest refractive index. Okay, diamond have a highest refractive index. In nature lah. Okay, I want to stress that highest refractive index in nature. If I'm not mistaken, they are synthetic material. That means they are human made. Okay, material that is made by human that have higher refractive index than diamond. Okay, I think God lah, if I'm not mistaken, I think God. Okay. Okay, so can understand the refraction of light and the refractive index. Okay. Okay. Okay, so next one, look at Snell's law. Okay, what is Snell's law? So we look at law of refraction of light first. Okay, the law of refraction of light refer to these two. Okay, the first one is that the incident ray, refracted ray, and normal meet at one point and are in the same plane. Okay, so like what is it that you can observe from here? Okay, the incident ray, refracted ray, and normal, they all meet at one point. Okay, that point is the point of incident, and they are in the same plane. Okay, what does it mean by in the same plane? In the same plane, that means is all three of them are on the same surface. Okay, all three of them are on the same surface. So, for example, okay, on the same plane, I try to explain here. Okay, what does it mean by on the same plane? Okay, one easy way to explain is that is on the same surface lah. Okay, on the same surface. So that means is like this. So let's say that we have okay, let's say that we have this is a piece of mirror lah, for example. Okay, let's say this is a mirror. Okay, let's say this is a mirror. Okay, so when the light, okay, when light shine on the mirror, okay, the light reflect like this. Okay, and the light reflect like this. So there is a normal. Okay, that go through the this point. Okay, so all three, the normal, the incident ray, and the refracted ray. So this is incident ray. This is the this is reflection. This is reflection. I explained on the same plane now. Okay, with using reflection. Okay, this is reflected ray. Okay, we are talking about refraction, but I explained what does it mean on the same plane using reflection. Okay. Okay, so what does it mean by on the same surface is that like this. So let's say that okay, that means like this. That means let's say that you have a piece of cardboard. Okay, you put like this. Okay, you put a piece of cardboard. So this cardboard is 90 degree with this mirror. Okay, 90 degree. Okay, with this mirror. So this incident ray is on this piece of cardboard, on this surface of the cardboard. This normal line is on the piece of cardboard, and then this reflected ray is also on that piece of cardboard. Okay, they all lie on the same surface. Okay, on the same plane. Okay, on the same surface like this. That means you will not have the light. Okay, the light will not like go in here. That means the light, this light is on this surface, and the normal is on this surface, but the reflected ray is outside of the surface. That means go into another direction like that. Okay, it will not happen that way lah. It will not happen that way. This one is wrong. Okay, it will not happen that way. That means all the incident ray, reflected ray, normal, all lie on the same plane, on the same surface. So this is okay. I explained using reflection. Okay, reflection. Okay, I explain using reflection, but it's the same for refraction. Okay, it's the same for reflection. That means the light that refract, the refracted ray, normal, and the incident ray, they will all lie on the same plane also, all on the same surface. That means when it refract, it will not bend into another direction like that. Okay? I hope that you understand what does it mean by all lie on the same plane. Okay? Okay, I hope this can help you understand okay, what does it mean by all lie on the same plane. Okay, if you got question, please ask okay? For question, please just ask Okay, so that is the first law of reflection. That means the incident ray, refracted ray, and normal meet at one point and are in the same plane. Okay, next is Snell's law. Okay, Snell's law states like this. The refractive index of medium 1 times the sine of the angle inside the medium 1, medium number 1, will be equal to the product of the refractive index of the second medium times the sine of the angle in the second medium. Okay? So rearrange, we get like this. So the refractive index of medium 2 over the refractive index of medium 1 equal to the sine of angle sine of angle of the medium 1, okay, over sine of angle in the medium 2, okay. All right. So let's try it out. So for example, here we have 3 examples here Okay, we have 3 examples. Okay, so the first one I already show you here. So for example, we have light propagate from water into perspex. Okay, go from water into perspex. So the incident, the refractive index of water is 1.33, refractive index of perspex is 1.5, and the incident angle inside the water is 50 degree, while the refracted angle is 42.8. So if we calculate, okay, using the equation, we'll be able to get on the left, that means inside the water is 1.02, and inside the perspex also 1.02. So they will be the same. Okay, this is just to show that the relationship is actually true okay. This can be obtained and proven in experiment, of course. Okay, we can just do experiment and we can get the angle, and then we will be able to calculate and see that they are actually the same okay. Okay, so let's try this one, the second one. So n1 sine theta 1 equals to n2 sine theta 2. Okay, so this is 1.33 sine 50 degree equals to, this is 1.66 sine of 37.9. Okay, so we will be able to get this Snell's law. Okay, this Snell's law, it says that incident ray, refracted ray, normal or meet at one point are in the same plane. Okay, Snell's law. Okay, it shows that this n1 times the the refractive index of the first medium times the sine of the angle inside the first medium equal to the refractive index of the second medium times the sine of the angle inside the second medium. So how is it that they get this? Actually, they get this from experiment. Okay, they get this from experiment. That means they do experiment with different substance, and this is the result that they get. Okay, this is the result that they get. All right. So from here, okay, we want to prove this one. Okay, we want to show that this one is actually correct. Okay, so we have 3 examples here. Okay, we want to show that this one is correct. So we have 3 examples here. So the first one we calculate and then we can get 1.02. Okay, that means this one N1 times the sine of angle 50. N1 1.33 times the sine of angle 50 degree equal to the N2 1.5, okay, refractive index of the perspex times the sine of 42.8 degree. Okay, these two will be equal. Okay, so we get that. Okay, this one multiply, you get 1.02. This one multiply, you also get 1.02. So they will be the same. So this will be the same for between water and glass, and also same for water and diamond. Okay, so this is the medium one is all water. But what if the medium is vacuum or air? Okay, if the medium is vacuum or air, so that means that why is it that we want to put vacuum or air? Because in vacuum or air, then the refractive index of vacuum or air is 1. Okay. See, okay, the refractive index of air is equal to 1. So if it is like that, that means that the refractive index of medium 1 is 1. Okay, so we can put like this. Okay, 1 over the refractive index of the medium. Okay, when we say the medium, it means like any medium that is other than air or vacuum then equal to the sine of the medium, sine of the angle in the medium, and over sine of the angle inside the air or vacuum. Then we flip, okay, because it's 1 over, so we flip, this one become N2, this one also flip. So sine theta 1 over sine theta 2. So that means like this, we can calculate. Okay, that means we can calculate the refractive index of medium. Okay, refractive index of the medium using the incident angle and the refracted angle. Okay, so that means if we use, that means we don't have to use the speed of light to calculate the refractive index. Okay, previously we learned that if you want to calculate refractive index, you need to use speed of light in vacuum over speed of light in the medium. But how do you measure speed of light? Okay, in that, let's say for normal people like you and me, okay, we are normal people. Okay, we don't have the sophisticated equipment, okay, apparatus to measure speed of light. Okay, so what is it that we can do? So if we don't have speed of light, that means we cannot calculate the refractive index of the substance, of the material. So this Snell's law shows to us that, oh, you can also calculate the refractive index just by using the angle of the light in the medium and in the vacuum. So you no need to use speed of light. Okay, get the idea? So we get this equation lah. Okay, refractive index of the medium equal to the sin I over sin R. So this sin I, although it says that this is incident angle, but this incident angle, it must be the angle inside the vacuum or air. This refracted angle R it must be the angle inside the medium. Okay, it cannot be the angle in vacuum or air. Okay, it must be the angle in the medium. This I must be angle in the vacuum or air. R, this one angle of the refracted angle, it must be angle inside the medium. Okay, get the idea. Okay, why we stress like that? Because this equation can also be used when the light come out like this. Okay, you see when the light come out from the glass, for example, or from the medium, the refracted angle will be larger than the incident angle. Okay, but even though like this incident angle, you must put this angle. That means this R and this angle we must put on top here, because this R is the angle in the vacuum or air. This I is the angle inside the medium, so we put here. Okay, I think I explain by using example. Okay, so for example, like this. Okay, so this is normal. This is normal. Okay, so let's say that we have light. Okay, let's say we have light like this going in, go here, and the light come out like this. Okay, the light come out like this. So this angle of this is incident angle, this refracted angle. This incident angle, this refracted angle. Okay, right. Okay, so when you want to calculate the refractive index of this material, okay, this glass or perspex or whatever lah, okay, when you want to calculate the refractive index of this material, by using the angle, okay, that means on top here, when go from air, okay, this is air or vacuum into the material. Okay, so from air go into the medium, the refractive index will be sin I over sin R like this. So this angle put here, this angle put here. But for here, over here, n equal sin I over sin R. But because this R is the angle inside the air or vacuum, so that means this one you must put here. This angle, although it is angle of incident, but it is the angle that is inside the medium, so this one you must put here. Okay, get the idea. Okay, I hope by showing you this, you can be clear about what it means by the angle of incident. That means the sin I, it must be the angle in the air or vacuum. Sin R, the R must be the angle inside the medium. Okay? Okay. Okay, so this one, when angle of incidence equal to 0, what happened? When angle of incidence equals to 0, that means like this. When the light go in straight along the normal, then that means the angle of incidence is 0. So when angle of incidence is 0, then the angle of refraction also will become 0. Okay? So when this kind of thing happen, do we have refraction of light or not? The answer is no. We do not have refraction of light. We don't say that the light is refracted. Why we don't say that the light is refracted? Because there is no change in direction. No change in direction. So we say that no refraction. Okay, so this is the same as in other kind of wave. Don't care whether it's a water wave or sound wave. If there is no change in direction, then we take it that there is no refraction. Do the speed of the wave changes when go from air into glass block and back to air? The speed got changed or not? Yes, the speed got changed. When the light go from air into the glass block, the speed of light change, becomes slower. When go from glass block back into the air, yes, it becomes faster. The speed of light got changed. But direction got changed or not? No. Direction, no change. So if no change in direction, then that means no refraction. So we refer back to the definition of refraction. Okay, refraction of light is change in direction of light. Okay, there must be change in direction. If there's no change in direction, then we say that there are no refraction. Okay, get the idea. Okay, so I'm not going to discuss the experiment. The experiment not going to discuss because whatever that you can learn from this experiment, you already can learn from the theory. That means what we discussed just now, we already learned is the same thing. Okay, what is the value of refractive index? State one precaution need to be taken. So this is something that the knowledge that you only need in your practical. Okay, in your practical test. So I leave that to your teacher in your school. Okay. Okay, so real depth and apparent depth. Okay, so let's look at this real depth and apparent depth. Okay, so this is this is a phenomena that occur due to refraction. Okay, due to refraction of light. Okay, real depth and apparent depth. Okay, so refraction of light can cause object in water to appear closer to the surface. Okay, so that means when you look into water, when you look in look through a glass, the object that is under the glass or the object that is under the water, it looks like it is closer than it actually is. Okay, it looks like it's closer. Okay, so let's draw a ray diagram to show the real depth and apparent depth. Okay, so this one, I hope that if you have printer, you can print out this page. Okay, you print out this page only also can. You print out this page and then you draw using your ruler. Okay. Take out your ruler or pencil, or you want to use pen also can, but I prefer that you use pencil because if pencil, if you draw with pencil, you accidentally you draw wrongly, then you can just erase. Okay. All right. So this is what happened. Let's say we have a glass block. Okay, this glass block is very thick, 8 centimeter thick glass block. So we have a coin. Okay, we put a coin under the thick glass block. So what happened to the light from the coin? Okay, what happened to light from the coin? The light from the coin propagate through the glass block and come out. So you see, when the light come out, it will be what will happen to the light? It will refract away from normal. You see or not? Okay, the light at first supposed to go straight. Okay, the light is supposed to go straight like this, but the light bend this direction. So that means the direction of the light changes. There is a refraction. So it refracts away from normal. So why refract away from normal? Because it propagates from medium of higher optical density to medium of lower optical density. So that means the speed of light increase. Okay, the speed of light increase, so it bend away from normal. Okay, bend away from normal. So when you look at so it bend away from normal and the light go into your eye. Okay, this is your eye. Okay, the eye of observer. Okay, so okay, now we draw another ray. In order to find out the location of the image, we need to draw two lines that represent the light ray. Okay, so this coin, okay, light that come from this coin, let's say that it go to this point P prime, okay, P prime, and then it go out, it refract. Okay, refract and bend away from normal also. Okay, bend away from normal also. Because go from medium of higher optical density to lower optical density, so speed of light increase. So bend away from normal. Okay, so when the light bend and then go into our eyes, so from our point of view, okay, from the point of view of the observer, it looks like the light come from where? It looks like the light okay, it looks like the light come from here. You see this point or not? Okay. Looks like the light come from here, from the point of view of the observer. Okay, from the point of view of the observer, it looks like the light come from here, this point. Okay, looks like the light come from this point. Okay, we use dotted line to show that the light looks like come from here. Why we use dotted line? Because the actual light is here. This is the actual light. Okay, this one here, this line here, this dotted line here, is there? Here got light or not? There's no light here. Okay, there are no light. but it only looks like the light come from here. Okay, actually the light come from here, but from the point of view of the observer, it looks like the light come from here. Looks like okay, looks like the light come from here. So if it looks like the light come from here, that means this coin, it will look like the coin is here. Okay, it will look like the coin is here. Get the idea? Okay, it will look like the coin is here. Okay, so this is the image. Okay, this one O for object. This one we label as I for image. Okay, I for image. So it looks like the image is over here. Okay, and if the image is over here, okay, if the image is over here, so that means it will look like if the image is nearer compared to the actual object you see or not? Okay, actually the object is under the glass 8 centimeter, but it looks like but due to refraction, it looks like the coin is here. So that means the coin will look like nearer to the surface and bigger okay, bigger, nearer, then it will look bigger, right? Okay, nearer, then it will look bigger. So this here, okay, okay, so this here, 8 centimeter. Okay, this 8 centimeter is the actual depth. Okay, with the symbol of capital H. Okay, with symbol of capital H. Actual depth 8 centimeter. And then this one here, okay, here to here. This one here will be the apparent depth. Symbolized by a small h. Okay, so actual depth is here, apparent depth is here. Okay, so this is apparent depth. So that means actually the coin is 8 centimeter under the glass block, but it looks like the coin is okay, how many centimeter is this? We can try to measure. Okay, more or less okay, let's say that 3.5 okay, more or less okay, this is example okay. That's why I say you want to I hope that you can print out this page okay, you print out this page and then you draw it yourself. Okay, you draw all of it, draw the normal, draw the incident ray, refracted ray, draw the dotted line, find out where is the image, take a ruler and measure the apparent depth. Okay, but okay, let's say the apparent depth is let's say 3.5 centimeter okay, let's say it's 3.5 centimeter. Okay, let's say it's 3.5 centimeter. So that means it looks like the image is 3.5 centimeter under the glass rod. Okay, then the image will look like it's bigger lah. Okay, looks bigger because it's nearer to the surface. Okay, get the idea. Okay, so we found out that we can also calculate we can also calculate the refractive index of the medium by using the real depth and the apparent depth. Okay, so for example here, the real depth is 8 centimeter. Apparent depth is 3.5. So we can get that we get 2.29. Okay, 2.29. The refractive index of the glass is 2.29. Okay, on this glass, okay, on this example, okay, is 2.29. Okay, so you see that there are until now, okay, that we already learned 3 methods of calculating the refractive index. The first one is original method. That means we use the speed of light in vacuum over speed of light in the medium to calculate the refractive index. This is the original one. And then after that, we found out that if we use the angle also can. Sin I over sin R also can get the refractive index. And now we learn the third method. Okay, we use the real depth and apparent depth also can get the refractive index. Okay. Okay, so this is real depth and apparent depth. Okay, we discuss one example here. Okay, one situation example here. Okay, so we have a diver inside a water. Okay, under the surface of water, and what happens when the diver when the instructor look at the diver? Okay, if the instructor look at the diver, that means the light from the diver go to the instructor, right? Okay, the light from the driver go into the light of or go into the eye of the instructor. So from the point of view of the instructor, it looks like the light come from here. So the instructor will see the diver is over here. Get the idea? Okay, we see the diver over here. The reason is, of course, when the light go from water, which have a higher optical density, into air, which have a lower optical density, the light will refract away from normal. Okay, it refract away from normal, it bend away from normal, and go into the eye of the instructor. So from the point of view of the instructor, it looks like the diver is over here. But actually the diver is over here lah. Okay, so if that is the case, then the diver looks closer to the surface by instructor. Okay, so the explanation: light travel from water into air, light refract and bend away from normal. So image of diver appear closer to the surface. Okay. Now the other way around: if the diver look at the instructor, so the light from the instructor go into the eye of the diver. So what happens is the light from the instructor go from air inside the water. Okay, go from the air into the water. So that means the speed of light will slow down and the light will refract towards normal. Okay, it will refract towards normal. So from the point of view of the diver, okay, from the point of view of the diver, it looks like the instructor is further away, higher up. Okay, it looks like the instructor is over here. Okay, from the point of view of the from the point of view of the diver, it looks like the instructor is over here lah. Okay, like that. So instructor looks further away my diver. Okay, so light travel from air into water, light refract and bend towards normal. So image of instructor appear further away from surface. Okay, so here we have another experiment, experiment 6.2. So this experiment is the experiment for to investigate the relationship between real depth and apparent depth. Okay, again, this experiment I also not going to discuss because same reason. What is it that you are going to learn from this experiment? You already learned in the theory lah. Okay, this experiment, the important thing that you need to learn from this experiment is actually the technique. Okay, that means the non-parallax method. Okay, this technique. This technique you can only learn if you do the practical. Okay, you do it practical, then only you can get this. You can understand and how to use this technique, the non-parallax method. Okay, so since okay, so we want to go to solving problem involving refraction of light. Okay, so let's look at the examples. Okay, figure 6.14 show a light ray traveling from air into a plastic block at an angle of 60 degrees. The refractive index of plastic is 1.49. Calculate angle of refraction R. Okay, so we have the refractive index. We want to calculate the angle of refraction, and we also have this one 60 degree, which is the incident angle. So we can calculate the angle of refraction by using Snell's law. Okay, n equals to sine I over sine R. Okay, so this is 1.49 equals to sine 60 degree over sine R. So this R is the one that we are looking for lah. Okay, so you will get 35.5 degree. Okay, 35.5 degree. Okay. Okay, let's look at the next one. When a coin inside a beaker containing a solution is observed, image of the coin is seen at a height equal to 2/7 of the depth of the solution. Okay, what is the refractive index of the solution? So this is involve the depth. So that means this is we calculate the refractive index by using the real depth and apparent depth. Okay, so in order to let us have a more clear idea of what the question is talking about, so basically it's like that lah. Okay, so let's say that we have a beaker. Okay, there's a solution. Okay, so image of the coin is seen at the height equal to 2/7 of the depth. Okay, so that means if this is 7, okay, let's say that the coin, the actual coin is here, the object is here, but the image looks like here. Okay, this is the image. So this one 2. This is the image of the coin is seen at the height equal to height of the depth. Okay, sorry, at a height. So that means is here. This is the image. Okay, so this is 2/7 or if this is 7, so that means this is 2 lah. Okay, like that, equal to 2 over 7 of the depth seen at the height. Okay, the important word here is the height here. Okay, height. So you have to read the question carefully lah. Okay, because a lot of students they confuse. Okay, sometimes they say at the height of, at the depth of, if say at the depth, so that means it's here lah. Okay, 2 is here. If it's height, that means from the bottom here. Okay, what is the refractive index of the solution? So because if this is the case, so that means the apparent depth is here, which is 5. So that means if you want to calculate the refractive index, then real depth over apparent depth, then the real depth is 7, the apparent depth is 5. Okay, so we can get it is 1.4. Okay, the refractive index is 1.4. Okay, for information, refractive index is a number. It has no unit. Refractive index have no unit. It's a ratio. Okay, refractive index is just a ratio that show the comparison between two values. Okay, so it has no unit. Okay, next let's look at this exercise. Okay, figure 6.16 show the path of light which travel from medium 1 to medium 2. Okay, write an equation to relate the light that travel through the medium. Equation, so I believe that is referred to the, because the question will give us the angle. Okay, so we can use the Snell's law. Okay, use the Snell's law. Okay, so N1. Okay, refractive index of medium 1 sine 75 equals to N2 sine 55 degree. Okay, so this is the original Snell's law. It's like this. Okay, and there are the reason why I use this instead of the N equals to sine 1 over sine I over sine R is because sine I, if N equals to sine I over sine R, this I, it must be in air or vacuum. But here it doesn't say anything about medium 1 being air or vacuum. Okay, it doesn't say that medium 1 is air, it doesn't say medium 1 is vacuum. So we cannot use N equal to sine I over sine R. Okay, get the idea? Okay, so write an equation to relate the light that travels through the medium. Okay, so B, determine the refractive index for medium 2 if the speed of light in medium 1 is 3 times 10 power 8 meter per second. Okay, so determine the refractive index. Wait a minute. Determine the refractive index for medium 2. Oh, okay. So what it's trying to say here is that the speed of light in medium 1 is 3 times 10 power by 8 meter per second. So it means that the medium one is vacuum lah. Is vacuum or air. Okay, because this is the speed of light in vacuum or air. Okay, so if that is the case, then that means we can use n equals to sine I over sine r lah to calculate the refractive index for medium 2. Okay, so because this n1, okay, will be 1. Okay, sine 75 equals, this one is the refractive index of medium 2, is sine 55 degree. So we get n2 equals to, okay, so we get it to be 1.18. Okay, so this is the refractive index of medium to 1.18. And then C, we want to calculate speed of light in medium 2. Okay, so refractive index equals to speed of light. Okay, the symbol C is the symbol for speed of light. Okay, so speed of light in vacuum, okay, over this one, speed of light in the medium. Okay, so 1.18, 3 times 10 power by 8. So the speed of light of the medium equals, okay, so it will be equal 2.54 times 10 power by 8 meter per second. Okay. Okay, next. Figure 6.17 show a tank filled with oil to a height of 3 meters. The oil has a refractive index of 1.38. Okay, filled with oil to a height of 3 meters. The oil has a refractive index of 1.38. What is the apparent depth of the tank as seen by the observer from above the tank? Okay, so refractive index is real depth over apparent depth. So the real depth, so the refractive index is 1.38. The real depth is 3 meters. So the apparent depth equal to, okay, so is equal to 2.17. Okay. 2.17, okay, 2.17 meter. Okay, so number 3, figure 2 show a glass block with a refractive index of 1.5 placed between the eye of the observer and the object P. If the thickness of the glass is 30 centimeter, what is the distance between object P and its image? Okay, so so the image will be nearer to the observer lah. Okay, so let's say this is the image. Okay, let's say this is the image. So that means here this one 30 centimeter is the actual depth, and this one here to here is the apparent depth lah. Okay, this is the apparent depth. So we calculate the apparent depth. Okay, so refractive index equals to real depth over apparent depth. So give that the refractive index is 1.5. So the real depth is 30 centimeters. So the apparent depth is Okay, it will be 20 centimeter. But the question wants us to find the distance between object and image. That means we want to find out this distance. So distance, okay, we can just use a symbol of small d to represent the distance. So it will be 30 minus the 20 centimeter. So it will be 10 centimeter lah. So the distance between the object P and the image will be 10 centimeter. Okay. So this topic 6.1 we stop here lah. Okay.